Okay, so in Atmega 128, there are two pins that are used specifically for transferring and receiving data serially. And these two pins are known as TX and RX, receiver and transmit. And they are part of the port, which we are going to see in a minute. So these pins are TTL compatible, so therefore they will require a line driver to make RS232 compatible. And generally, we use MAX232 chip. So MAX232 chip is used to convert the voltage level between the direct RS232 connector and standard TTL. So you can see MAX232 is in between the Atmega 128 and the DB9 of the RS232. So inside of the MAX232, you can see that transmit and receive pins. So we have to be careful when we are connecting in the Atmega 128. Maybe you can use, so if you are using D zeros, so you have to use port E0 and port E1, RxD0, so that has to be connected to the transmit side. So null modem connection is working over here. And the TXD0 has to be connected to pin 12, which is R1 out. Okay, and on the other side, pin 14, which is a transmit 1 out, is connected to the receive pin of the DB9, and the R1 in is connected to the transmit pin of the DB9. And it's just demonstrating a typical null modem connection. So in AVRs, we have got two users connections. And it is known as user 0 and user 1. And they can be in normal mode, normal asynchronous, double speed asynchronous, master clock synchronous, and slave clock synchronous. But in this course and in this chapter, we'll concentrate on the asynchronous mode. We are not going to consider synchronous modes here. So AVR can have full duplex operation with configurable high resolution baud rate, serial frame sizes. You can have one or two stop bits, odd or even parity bits, and frame error detection and multiprocessor modes. So AVR is offering us a lot in embedded systems if we want to use USART. And there are also three interrupts in AVR that can handle USART communication: transmit complete, transmit data register empty, and receiver complete, which I'm going to show you in a minute. And another important thing is AVR has got 5 registers, which is related with the USART, and UBRR, which is the baud rate register. So when we do the calculations, we have to set the baud rate register, what will be the value in order to do the communication or establish the communication. UDR is the data register. So whenever you want to send the data in full duplex serial communication, there are actually two shift registers, which is known as transmit shift register. Maybe I can show it somewhere. Okay, maybe in a minute. And we have got transmit data buffer register and receive data buffer registers, and the user transmit data buffer register. They use share the same I/O addresses, which is called UDR. And when you write data to UDR, it will be transferred to the transmit data buffer register. And when you read data from UDR, it will return the contents of the receive data buffer register. So Serial port interrupts, we can have a transmitter side, which we send one bit at a time. So whenever it is completed, so interrupt is raised when the transmitter is empty. So we don't have anything in there. Interrupt will be raised here. So a byte has been transmitted and next byte ready for loading. And on the receiver side, receiver interrupt is raised when receiver is full. So whenever it reaches there, okay, I have received my data, next byte ready for loading. Okay, so that's what we are looking when we are generating interrupts, or actually AVR is looking for. So the organization of the or the architecture of the user side of the AVR, we have got clock generator, which is active in the synchronous modes only. So I'm not going to go into the details of that. So the transmitter side is over here, UDR register, which I already mentioned, is connected directly to the data bus. And transmit shift register will shift out the data. Okay, and if you want to add a parity generator, if you do remember from logic design, you can use a parity generator, or without a parity generator, the multiplexer chooses in between. And TX control, the transmitter controlling and sending out the data. So on the other side, we have got the receiver part, where we have got the receiver pin RxD, receiver control register is over there, and we have got the pin controls. So if we are using clock, we have to be careful over there. Data recovery and parity check, we have to put them into a separate registers. Then when we have got the data recovery, we have got again the UDR receive side. So you can see that received data will be shifted into the UDR and then to the data bus. Okay, so we have got UDR on both sides, and we have got transmit shift register and receive shift register, which are the buffers. And these are the three control register, UCSR-A, UCSR-B, and UCSR-C, that we are going to see how they can be configured in order to perform the required communication. So one of the important thing is AVR user clock generator or baud rate generators, because we have to use them carefully in order to send the data. So UMCell in UCSR-C, control register C, selects between the asynchronous and synchronous modes of operations. U2X is used to choose if you want to double the speed of the transmission in asynchronous mode. You can double the speed. There's a, as you can see, the clock divider scaling down, so the UBRR. And UBRR is the baud rate register that we are going to see in a minute. So how is that UBRR is calculated? Two sides has to agree on the baud rate. So these are the baud rates of the hyperterminals that we generally use in order to send data from the microcontroller to the PC. Now the down counter runs at system clock to count from UBRR value to 0. Like in the timers, if you do remember, it was counting up. Now this is counting down. Then it loads UBRR again, and each time it reaches to 0, baud rate clock generator is generating the clock. So we have modes, again, asynchronous normal mode, which we generally use, which is U2X is not activated. Double speed and synchronous master modes, which we are not going to consider at all. So if we are using double speed, we have to divide by 8. If we are using normal mode, we have to divide the oscillator, the frequency of the oscillator by 16. And we can easily find out UBRR value that we need to load into our register. So UBRR, as you can see from here, there's a UBRR which is 11 down to 8 and 7 down to 0. It's 12 bits. So when we configure it, we can actually decide. We can actually use it as a 12 bits, and we have to use the low byte or high byte of the UBRR to load in. So we can also have some errors because actual baud rate setting is an approximation. So you might get an error. In order to calculate the error, we have to use a calculated value and the integer part of the calculated value divided by the integer part, which will give you the error. And also you can have the calculated baud rate minus desired baud rate divided by the desired baud rate. That will also show you how much error you are having in your calculations. So the frame format in AVR, we have got the start bit, which is bit 0. Then we have got the data bits. They can go up to 8 or 9 bits. Then you can have as an optional parity bit, can be even or odd parity. And we have got stop bits, 1 bit or 2 bits, which is always high. And then it goes back to idle. No transfers, nothing. And the parity bits, as you do remember, if you do remember, we have to XOR the data bits in order to have the parity bits 1 or zeros. Sorry, odd or evens. So in AVR, we can detect frame error. So it can set an acknowledgement or not acknowledgement, and then frame error occurs when the receiver is expecting a stop bit but does not find it. So it can resend the data. And data overrun error, data was not removed in the receiver buffer because as we are shifting them out, and another byte comes in and overloads that one. So this is data overrun. So what you can do while you're writing a code, you have to make sure that your receiver is empty. You have to check it that your receiver is empty, and then you start the transfer for the next byte. So let's get into the details of these registers. UDR, as I already mentioned, we can do the data register, which can perform transmit and receive data buffers, share the same IO address UDR0 or UDR1. 5 to 7-bit character settings, upper unused bits will be ignored by the transmitter and set to zeros. And transmit can only be written if UDRN flag in the UCSRA register is set. Otherwise, transmitter ignores data written to the UDRN. So it has to check it, and then it will do the operation. So the control register A, this is the one which we have to check. RxCN, user receive complete. There's unread data in the receive buffer. So enable with receive mode and can generate receive interrupts. So we have received data, we have to copy it to somewhere else. Transmit complete, entire data is shifted out, and it can generate an interrupt as well. UDRN, user data register empty. We can check if the data register is empty, then we can activate to receive a new data. We also have error bits like FEN, which is a frame error. DOR is a data overrun error, which we already mentioned, and UPE is the parity error if there's a parity problem. So U2XN, if you want to double the user transmit rate, you can use this one. You can set it to 1. And MPCM is the multiprocess communication mode. So some frames will be ignored if they do not have correct address information. Then user control status register B. So if you want to enable interrupts, we have got receive and transmit interrupts. We also have UDR is empty interrupt, which we need to enable these if you want to expect an interrupt from them. RxCN receiver enable. If you want to operate the receive function, then you have to enable this one. If you want to operate transmit function, you have to enable that one. If you want to operate both of those, that means they both need to be enabled. And UCSZ and 2 is the character size. So you will see in a minute that you can have 8-bit characters or 7-bit characters. It will be joined with some other bits in other registers. So it sets the number of bits used by the transmitter and receiver. And if you want to have the a larger data packet, then you can have two alternatives over here, two separate bits that you can, that will be the 8 or 9 bits will be stored in these registers. And the control register C, we have got UMCell, so the mode select, asynchronous or synchronous. Parity modes, disabled, odd parity, even parity can be selected. USBN is stop bits, 1 stop bit or 2 stop bits. So 0 for 1, 1 for 2. UCSZ is the character size. So these two, which was combined with this one. So if you want to have a character size 5 bits, 6 bits, 7 bit, 8 bits, or maybe 9 bit, then you have to configure it and the clock polarity in this synchronous mode, which we are not interested in. Now, how do we configure the AVR in order to perform a receiving and transmitting? So that's what we are going to see next. Now, in order to receive, first the UCSRB control register B is loaded with the value X10 to enable user receive. So how do we do that? X10 means 0 hex 10 is 0001 000. So we are just enabling RxN bit over here, and the rest are not enabled. This is what we are doing with 10. Then UCSRC register is loaded with hex 06. So 06 is 0000 and 0110. Now hex 06, this is going to be asynchronous mode. So UPN's parity mode, if you don't want to set anything, you just place them to 00. And then USBSN stop bit, you can have one stop bit is enough. Then you choose how many bits. Generally, we choose 8 bits of data, standard package. So 1 has to be placed over there. And then we have got 0 on that side. So that's why we have got 1 to select 8-bit. Then UBRR is loaded with the proper value to set the baud rate. So we have to do the calculation and we have to set the baud rate. And then in A, we have to monitor the receiver flag, either using a polling or using an interrupt. So you can enable the interrupt, and whenever you receive an interrupt, in order to enable the interrupt, you have to enable bit 7 in the control register B. And Then when you receive the data, UDR register has the byte when this flag is raised, and we have to move the content to somewhere else to avoid overwriting it. And then we go back and we can look for a new data to come in. So the transmitting part is also similar. Now on the transmitting part, we have got 0 hex 08 that needs to be set for control register B. So what we are enabling the transmit over here. Okay, and the control register is loaded with the value, control register C is loaded with 0 hex 6. Now in this one, again, 8-bit data that we are going to use and nothing else will be set. That's why we set it to hex 6. No parity, one stop bit. UBRR value has to be set, and we have to place the byte to the UDR register, and we have to monitor if it's empty, and we have to make sure that the TXCN flag is raised. Again, we can use interrupt, or we can use polling and we can check it. Then we send the next character. The best way to understand these are to do some examples at the end of the chapter. So let's do those examples to see how we can use USART with AVR. So it says 8 megahertz, write a program to transfer the letter G serially at 9600 baud continuously. Okay, so before we do anything else, we have to find out the UBRR value. Now we have got 8 megahertz divided by 16, because we are just doing a normal mode transmission. So this is going to be 500 kilohertz divided by 9600 baud minus 1. So this will give us, it's coming from the formula, by the way. We will have 52.08 minus 1, which is 51.08. And we can do an approximation of 51 over there. So this is the value that we need to load. And 51 in hex is 0 hex 33. This is what we need to load in UBRR register. Okay, so as we are going to do a transmit, then UCSR has to be UBRR 0. So UCSR 0 B will be 0 hex 08, and UCSR 0 C, it's going to be hex 6. So there's no one stop bit, no parity. So we have got C, and in order to, then we have to monitor A. We don't need to set anything over there. So these are the registers that we need to set in order to perform the operation. So let's write the code for it. Once again, dot include m128def.inc. So first thing to do, let's do the control registers, and we can say LDI R16 1, which we need to enable TXN 0. So we can say enable transmitter. And that has to be sent out to UCSR0B, which is going to be R16. Then we just repeat the same thing, LDI R16. We have to enable UCSZ bits. So 1 UCSZ01 and UCSZ00. So this is going to be an 8-bit data, no parity, 1 stop bit. And then now one thing that we need to be careful, UCSR0C is not in the IO register. It has to be called with STS. So UCSR0C. It's actually in the IO register, but let's use out. It's in the IO register, but we can just have it like that. So there's no point of going other way around. So that will be set, and then we have to set the UBRR. So LDI R16, it's going to be 0 hex 33 that we have calculated. And this is just going to be in the low byte. UBRR0L will be R16, and there's nothing else we need to load in the high byte. So 9600 baud, 8 megahertz clock. So now we are ready. As we are not using interrupts, we have to use polling to check. So SBIS UCSR A 0A UDRE 0. So we have to check, is UDR empty? Because if it's not empty, we have to wait until it's empty. So R jump again. And then if it's empty, then LDI R16 initialize the ASCII character that we would like to set. Send G. And where do we need to place? Out UDR 0 R16 to UDR. And once we are done, R jump again. So we can repeat this, do it again and again. Okay, so you can find a similar solution. What I was trying to say over there, you can use an address like this defined, and you can use STS over there, but if you just want to use UCSR0C, that's also fine. So another one with a C program. So 8 megahertz, write a C program to initialize the user transmitter work at 9600 baud. So we will get the same baud rate. So UBRR will not change, 1 stop bit, and that's it. So it's just an initialization, and there's nothing over there because it's going to be a transmit. It's similar to what we have done. TXDN pin bit has to be set, UCSZ01 and UCSZ00 has to be set in UCSR0C, and UBRR has to be set. So we can do the calculations over here as well. We can define the frequency just to parameterize everything. We can put the baud rate, define baud rate, and we can do the baud rate calculation by using the same formula that we have got here. Okay, so this is the same formula. You can do that in the program and it will do it automatically. So if you want to change the frequency or if you want to change the baud, you can just change those two parameters and it will do it for you. So UBRR 0H, again, this is coming from the BR calculation, baud rate calculator. So you can just place those parameters in there. And the control register B is just enabling the transmitter. C is selecting 8-bit data, and UBRR 0L, which we will not require because we already did that, so you don't need that line over there, and that's all you need to have. And the last example, sorry, the one before the last is writing the same example that we have done over here by using a C code. So it's the same thing, initialization for the initializing transmit 8-bit data, hex 33 for 9600 baud. Check if UDRE0 is empty in the UCR control register A, and then we send the character. So over here, we can use in the main, we can initialize the user and we keep send the character. That's all we need to do. So we have seen these are just using the polling. We can modify the codes and we can have it using interrupts. One thing that we need to be careful with the interrupts, which interrupt are we going to use? So in this case, in this example, we are going to receive a bytes of serial data and we have to put them on port B, set baud rate at 9600, 8-bit data, and one stop bit. So that means these are all going to be same. Okay, nothing will be changed here. So let's modify that code and we can write the same thing. Now, one thing that we need to be careful is we have to define the addresses for the interrupt, as we are going to use receive interrupt. So maybe we need that table over here. So .org 0. So address 0, we have to jump jump main, and then .org. So we are going to use receive complete. So the receive complete is here, which is hex 24. So we can have 0 hex 24. And we can say rjump useart receive complete ISR, interrupt service routine. So let's call it that way. And then we can say the main will start at address x100. So we are in the main and we can initialize the stack as we are using interrupts. So I can just use the macro initialize stack, and then once we initialize the stack, as we are going to do a receive, there are a few things that we need to modify now. Now in UCSR0, this is going to be RxN, as we are going to do a receive. And also, we have to set the enable interrupt. We have to enable the interrupt so that we can receive an interrupt. RxC interrupt enable 0. So enable receiver and interrupt. Then this will be sent to UCSRB. 8-bit data, no parity. This is not going to change. And UBRL, so that's going to be baud rate, hex 33. Nothing will be changed over there as well. And then we can use global interrupt enable as well, because we have to enable it. Enable interrupts globally. So then we can define also, because we are going to send the data to port B, LDI R16 0 hex FF out DDRB R16 set port B as output, and all we need to do is wait over here. Now while we are waiting, if the interrupt comes in, we have to have the ISR ready for it. So this is going to be user receive complete ISR. So we don't need to use polling anymore. And we just need to check what is loaded. So in R17 UDR0, what we have received. So copy UDR, whenever the interrupt is received, copy UDR to R17, and then out port B R17, and then red I, return from interrupt, and that's it. So the modification that we have done is allowing the interrupts so that we can wait for an interrupt rather than going for a polling and checking again. Receive interrupt is hex 24. We modified the control register B, enabled the receiver and receiver interrupt. We also enabled the global interrupts, and in the ISR, we just got the value from UDR, loaded into R17, and sent it to port B. So that's all you need to know about the serial port programming. If you know how to control the registers or configure the registers, then the rest is pretty straightforward. If you have questions, please note them down and you can ask me during the live sessions. Thank you.